All right, then we will continue. I have to say that I am a little bit sorry. I think I have been very unclear with regards to the way of explaining collapse. Let me do it one more time. Maybe this time it will be easier to understand. I said that point 4 would interact with the yield. That would of course only be applicable for category collapse, yield strength collapse. Like I said, point 4 and these curves, they will be subtracted for the buckling tendency that you find with the pipes, meaning if you find pipes with a DT ratio close to yield strength, number 4 would be slightly on the inside. For pipes on the right hand side, you will find a flat line, but it will be coming up quite a bit from the yield. We see the curve here, and the further you are to the right, the further away or up here you will find the collapse resistance. But again, only 3 curves. Yield strength, which is represented by 1 Mises. Plastic and transition collapse will have a curvature on the inside of the yield strength here, and when it comes to yield strength itself, it would follow the 1 Mises, and point 4 would be on the intersection here. I hope that clears up the question about collapse, and I'm sorry for the confusion. I hope that is okay now. We will jump to casing design regulations, and hopefully we will also have time for casing wear at the end of this lecture. Casing design regulation, they are there to help us do the right thing according to, call it, the company philosophy. When it comes to all types of regulations, anywhere you find yourself in the world, there will be a set of regional requirements, and they would typically be less specific. They would give you a very wide frame of what is okay. In Norway, how it's done, they typically points towards industry standards. So what the governing official regulations are. They say you have to, for example, do a job in a specific way with the hard line that you are considering the environment and so on and so forth, as exemplified in NORSOC, and then it will point to some NORSOC standard and say that this is one way of doing it. So the NORSOC would be more specific, the same with the ISO and API. And remember, this is important. It's very easy, and I've seen so many students, they think that these standards are a way of explaining how things are done. They are not. They are exemplifying a way that would be okay to do things. Like said, when it comes to the wall thickness, it's said at some point that, and it was initiated by the casing manufacturing industry. They were saying that it's hard to do a wall thickness more accurate than 85% or something like this, 87.5%. So that's why the standard at some point in time said, okay, let's add 12.5% wall thickness reduction. Then we're covering everything. And the industry of pipe manufacturing was very happy. And that was a long, long time ago. It doesn't mean that all casing manufacturers were happy about it. Maybe they were much better than 12.5%. But it covered everyone. So you need to know what is the real case, and in many ways things are better. It's like a minimum standard what is described in these standards. Yeah. Below the industry standards, we have each company's governing documentation. I have put out here what is an official set of regulations. You can find them on the link below. At least you could. It's publicly available. You'll find that the Equinor's call it a framework, and on the bigger scale, the Equinor book. It has the fundamentals of everything, all the activities and value creation that Equinor is doing. It's described as like these are the things we do. We will do them this way. We will do them beneficial for the environment. We will create value for people and so on and so forth. And then under there you'll find technical requirements and the requirements to the work process, how we will do things. Typically very specific. And then underneath you will find what is called recommendations and guidelines and information for people to follow so that it's easy to plan and do jobs. Yeah, and the lowest level in the pyramid will be engineering designs, drilling programs, detailed procedures, equipment procedures, so on and so forth. And in here also you will find the result and the conclusion that you do from your casing design. Typically, casing design, you'll find very detailed descriptions in the requirements and technical requirements on how to do it and what you should do. There will also be some guidelines, but most of the things in casing design, the integrity is so important that companies will typically put them up at this level. Let's jump into it. Casing design regulations is kind of like a philosophy, and what you'll find is that a company would say that you will have to have a certain level of experience in order to be allowed to be the main person responsible for performing it, and you will have to do the industry do it in an industry recognized software. Something with a known, call it, you have to, to put it in another way, you have to understand the output. Where are the weak points of this software? What does it really mean? You have to understand and trust the results. Software is software, and you have to understand that the people who made it and the result of the software is okay. All components needs to withstand the maximum loads and stresses through the life cycle of the well. You need to have a full understanding of the formation properties, and you need to be able to calculate the kick tolerance. And that's for all sections that you have a BOP installed. Now, for sections before this, well control is very often tied to shallow gas or shallow water flow. These are things that comes from understanding the formation properties. You will get input from the subsurface department, and you will make your design such that you're able to handle a flow even without a BOP. That's typically done with a diverter, so you're leading the pressure out of harm's way into a secure area. Yeah. Recommendation very often is to do a triaxial design, and triaxial design factors to be calculated for absolutely all casings. That's what was put into the N10U governing documentation for casing design. Triaxial design factors as a minimum, isolating to uniaxial, absolutely not acceptable. Recommendation: verify the integrity of each shoe, meaning before you start drilling a full section, you need to know that the previous section is fully isolated. Doing an FIT is fine, then you get basically not much information to go on by from the formation. You just know that yes, it's strong enough. My shoe has the integrity enough to drill the next section. Whereas if you do a leak-off test or an extended leak-off test, you would know much more about the formation at the casing shoe. In many cases, these would be recommendations or requirements given from the subsurface department in what is called the statement of requirements. Mentioned earlier in this lecture series, what you will receive for every assignment or every well would be a set of input and also requirements, as in what to log in the different sections, anything from cuttings analysis until gamma ray, density neutron, whatever it should be. That's put in there by the subsurface department, who is your client, and you're the one accepting the assignment. And in some cases, they need information like a leak-off or X-lot. Statistic and dynamical load case scenarios. Load cases, there is a minimum set of load cases that each company defines, and you will have to do the full analysis for all of them. Now, there are two different design categories very often. One call it standard and one HPHT. And for HPHT, well cases or fields, the design of casing and tubing needs to be done in advanced software. You see, in the standard calculations, typically you'll find that a software like a stress check from Landmark, it calculates, it doesn't model the temperature. We see the curved red graph is the temperature modeled in the producing well, using the geothermal gradient. and it will tell you this is the temperature in the either tubing or casing that you're doing analysis design for. Simplifying how you model the temperature, a stress check is saying that it's the same as the reservoir, basically. A simplification that in situations where you have HPHD conditions, it will exaggerate the stress that you're having, and you would typically select tubulars that are yeah, too extreme. Yeah, and we have the same situations for injectors. Um, you will have a surface temperature all the way down to the reservoir, whereas advanced modeling software like WellCat from also Landmark will give you a more accurate temperature profile and give you a more realistic um, uh, situation or stress situation, and then you can select the more appropriate pipe. The basis for design, one of the things that needs to be clear in the statement of requirements or recommendation to drill from the subsurface department would be questions that you see here. What is the application of the well? Should it be a multilateral now or later? Should it be a slot recovery, meaning that you reuse parts of the well to reach other targets? What is the well objective? Production, injection, combinations of these? Evaluation programs like logging and testing, you need to know if there's drill stem testing to be done or something else. Well interventions, in some cases fracturing might be so extreme loads that they are the ones determining what kind of tubulars you need. Acid stimulations, they may actually influence the material selection and or the type of tubulars that you will have to install because of corrosion, for example. Then we always need to do a life cycle design. So we need to know, is this a well that is going to stay for 5 years or for 15 years? Yeah, all components of the well needs to be made analysis of in this regard, even the casing, hanger and wellhead system. Yeah, the lifespan of each component in the well. And then finally also we need to understand what is the company well abandonment strategy. We need to know also the parts from the subsurface department, anything that is related to formation, because when we do P&A, we make barriers that are completely going from competent formation over to good steel and solid internal plugs, like a full barrier. And then here are some questions that we typically ask ourselves, because basically they are the fundamentals of casing design and they are often mentioned in the regulations, so you don't forget any of them. You will get the formation top, so you know the strength and the prognosis of pressures and fracturing gradient. Very important for the kick tolerance, of course. Shallow gas we talked about, and water zones, pore pressures, where that's relevant, permeability. Gas gradient in the different zones, temperature prognosis, integrity, yeah, so on and so forth. H2S and CO2 would be very important because they both influence the material selection. Where there's squeezing salts or shale zones, squeezing shales. Reservoir invasion and damage, directional plan, including dogleg severity. Very often high doglegs would typically add casing wear, or could at least add casing wear of significance. Drilling fluid systems, the chemicals that we are using could in some cases influence our material selection. Of course, their density has a direct impact on what you're doing. If you're doing water-based muds, we need to ensure that we add biocids so we don't have any H2S development over time from bacteria, damaging both to equipment and certainly to people. So yeah, that's important. Cement, zonal isolation, regulatory requirements for cementing, as much as we need to take away any high pressures in the annulus or any zones yielding typically gas migration. Packer setting depth, production packer setting depth, and the planned fluid density is very important for us. Yeah, and we often have reference wells, offset wells that we look at to know what was the program there. So we have like a good starting point for our tubulars, selecting also setting depths in the different formations from many of these offset wells, and making it the first run to see, okay, let's try this design, does it work, or do you need to adjust either the setting depth of the casing or change the casing type entirely for each section. It's just a place to start your analysis, and then yeah, we need to know that we can pull the pipe, like said earlier. If your company says that you need to be able to pull 100 or 150 tons above the string's weight, you need to know that the string weight plus 150 ton is still within the hoisting capacity of the pipe. The sign factors, you will find them in the regulations. Typically, all companies would have a set of factors. You even find these in as recommendations in standards. I'm pretty sure you can find those in NORSOK D10. I cannot remember. They may have exemplified a few of these ones. They're not always going in so much in detail as what you see here. Another thing, when we are making a well path, typically our well path in a software is perfect. It makes a perfect vertical section, and then a perfect curved section into a perfect sail angle, so on and so forth. In reality, what we experience is something else. When we drill, there are ledges, there are stringers, we typically get the bit bouncing off a hard stringer following more soft formation, creating a local dog leg, so on and so forth. And in order to handle these local dog legs and call it the nature, a natural well path, we have what is called dog leg severity override. And in your casing design regulations, you will find a table like this for I guess most companies, and it would vary with the type of system that you are doing. If you're drilling with a 3D RSS or if you're drilling with a motor, yeah. So. Without mentioning the details here, because you can read them yourself, we will move on to what we already have seen before in our calculations of section design pressure, adding some pressure in order to be able to kill a well, and the result is what we call the section design pressure, what you will pressure test your BOP to, and what will be the highest pressure the casing will ever see it through during its lifetime. Theoretical value, of course, not real. That being said, what is important for you guys? When you design a well, remember some annually they can be bled off. And typically, the people working on the well site or on the platform offshore, they would read off the manometer either once or per day in wells with problems. Maybe once per week in wells with a small history of small pressure increase, typically coming from gas migration, and in most new wells, they where it has been established that that pressure is not increasing, it would be once per week or whatever it would be, company philosophy. So, and where things become a little bit more complicated is where you actually cannot read the pressure in the annulus. What has been, I wouldn't say a problem or a headache, but a theoretical challenge would be the B annulus subsea wells. There used to be no system for reading off the pressure in the B annulus, and what you had to do in your casing design was to basically design for what we call annular pressure buildup. And gas migration would be a bubble of gas that comes from any formation that are exposed in the annulus, and the bubble would retain its pressure and go up to the top of the B annulus theoretically, and the pressure would build up until the B the formation exposed, the weakest formation exposed in the B annulus would frack. These are the things that we need to consider, and there has been situations where the B annulus has had problems because of the frac increasing from the theoretical. This is way beyond the scope of this class, but it's advanced casing design and it's special cases. What we're talking about would be a situation where, for example, the formation collapses on the casing, and then the mud deteriorates so that the weight material becomes like a plug going into the casing, and you have a situation where the formation frac has increased quite significantly from the theoretical. Theoretical situation, but what you need to understand and what you should have in the back of your head is, can I bleed off the annulus, read off and bleed off, or is this a closed environment, a closed annulus? This is a very special case that you really need to consider. A well construction like that is a high risk. What we're looking at here would be connections. What we call premium connections would be gas tight. Non-premium would be not gas tested. There are different levels of testing equipment. I am not going to mention or go into detail for testing of equipment, but what you'll find is that it's from level 1 to level 6, meaning level 6 is vibrations and temperature cycles in combination with gas. I think level 3 is just pressure testing with liquid. That being said, we'll touch upon pressure testing later on, and I will talk more about it then. Kick tolerance. We see here the typical kick tolerance requirements. You'll find that it's 4 for most sizes. Of course, kick tolerance is only valid as a concept where you have a BOP installed. And we discussed earlier 8 meters cubic from 12.25 inch, typically going down to the reservoir. And as always, very often this is students tend to forget that this is a minimum. So any section should have 4 or more standard cubic meters. 4 cubic meters of kick should be the minimum what it can handle. Or for 12.25 inch, it should be 8 cubic meters or more kick that it can handle. Yeah. Casing wear. There would be something said about casing wear. You should model it, and you should typically do that in a software. Material selection is important in this situation. 13% chrome is a difficult case. We don't really have any software for modeling casing wear for 13% chrome. What we have, what the industry has developed, is something for standard carbon steel. Planned wall thickness loss should be included in all your load cases. And typically what you'll find when you're doing analysis is that a good software like Landmark from Halliburton, they are saying that your acceptable wall loss can be this, and then you have to that's in your plots and your curves as an option if you want it, and you compare to what you do in the application from Landmark called casing wear, where you are modeling casing wear. Typically you find what is the predicted wall loss. Casing wear modeling is actually a little bit on the edge, difficult, bordering to difficult. Very often what we see is that students, or well, not students, but professionals, they tend to fail not putting in the effort to do it correct. The software is good, but where it fails typically would be the users. Yeah. Yeah. So that being said about casing wear at this point in time, load cases, mandatory set. We have already discussed the two ones. We have seen this figure before. And now, just a few minutes for casing wear. What I'll do, I think you guys have seen the slides, at least they have been shared with you from before. So I'm just going to fly through this. This is a question mark. Why? Because a drill pipe, a piece of drill pipe would never be like this. It would be like this. Why? Because it's in tension. From this point where the neutral point is, then you will get compression and it will be on the outside. But the majority of the pipe would definitely be on the high side because of its tension. Think about that when you think about where the pipe is in contact with the casing and creating casing wear. And it's typically the tool joints that are touching, and the part of the tool joint that is in contact with the casing will be what we call the hard banding. It's a portion of the coupling, the tool joint, where it has been welded in some reinforcement in order to withstand wear from both casing and from especially abrasive formations. So it's like a two-edged sword where on one side the casing needs to be preserved, but you also need to preserve your drill pipe. So that's where hard banding science, like what the Trio in Stavanger are doing. Well, they are no longer called Trio, the company, but they are one of the real specialists on the worldwide basis with their alloys specially developed for good preservation of not only tool joints of drill pipe but also on centralizers, stabilizers, 3D RSS. I know Schlumberger used them a lot. Yeah. Theory about casing wear. What we see is the mechanics of two-body wear, and abrasive wear is where we are at. That's what we experience in casing wear in our wells. Adhesive wear, galling type would be more what we have for 13% chrome materials, and that's why it's a complete different mechanism going on than for standard carbon steel, and that's why it never gets correct when you try to apply the software for casing wear on 13% chrome material or other. There are other types of mechanisms losing wear. We are not going to cover them here because they are not part of the theory behind casing wear and what is in the software modeling casing wear. Basically, it is deducted like this: the volume removed per unit length of casing is proportional to the friction work that is done, where we have the frictional work and the specific energy to remove 1 cubic inch of material. That's the epsilon. And the frictional work done per foot can be expressed as the normal force, the frictional factor, and the sliding distance. The sliding distance being a point on the tool joint and how the circumference travels with 1 RPM. It would be the circumsphere of the tool joint. That is then the sliding distance. So you have to multiply with the number of total revolutions of the pipe, then you get the sliding distance. Now the wear factor would be the friction factor divided on the specific energy. The wear factor is a bag of so many factors, like the type of mud, temperature, how much cuttings would be in there, so on and so forth. But in the modeling software, what we do as a rule of thumb, we put in 5 in the wear factor 5 in our simulations. And what we very often see when we back calculate after logging wear, physical after the job, very often it's between 2 and 3. Yeah, that's like calling it a rule of thumb, but never use that as an absolute, of course. Yeah, and the volume removed would be the wear factor times the normal force times the sliding distance. We see the side force being extremely important in casing wear, and again I use this this drawing with the purpose earlier. Why? Because the highest tension is the most shallow in the well. The highest tension creating the highest normal force in a curvature. Yeah. We are these are the calculations done in order to predict the wall loss. It's an empirical formula based upon more than 500 tests in the lab, and it's quite accurate. The wear volume is a part of the work function, trying to make one expression for how the wall loss is, making it into a software-based model. And what we know is that since the casing wear, look at this picture on the right, it has like a groove inside the casing, and you can think about it when you initiate rotation, it's a point load because the pipe is resting at a point towards the casing. And once you have made a groove, you see that the contact area between the pipe and the casing is increasing. And that's what we are accounting for in this calculation. The correction factor is quite large to begin with, and then it becomes 1 at some point. Where it becomes 1 is what we call the contact pressure threshold. That is a specific pressure side force coming from the side force between the casing and the tool joint of the drill pipe. Now, at that point in time, you will no longer create more wall loss. The correction factor being 1, no more casing wear. So the casing wear here is from a test and verifying the correction factor and also what we have is calculations for wear volume. How much did you lose? Going back to this formula here, the wear factor, the normal force, and the sliding distance. It has to be calculated back to a remaining wall thickness that we are using in our casing design analysis. It is time. We ended up doing the basics of casing wear. What you can look for yourself is a simulation here and these are pictures from Landmark's application called casing wear, where we are modeling casing wear. This is from a class done at NTNU some years ago, where we did the full development of well design. You'll see here all the steps that are done and the key factors on it and how the results come out. There's no time to go through it now, and I'm not so sure we will be able to discuss it too much in the last lecture either. The software of casing wear, I think you guys will have to work on that once you become professionals. And if you have a specific interest for it, you can go into the computers at NTNU with the software installed and do an analysis yourselves. It's not that complicated, and you have these slides to help you to start. And should you have any difficulties, you can always contact me on my email, as some of you have done. Please just drop an email if you want to have any other questions too, or have any comments. All right. 2 minutes into your time, sorry about that. Raise your hand if you have any questions. If you don't, then see you for the last lecture on Thursday. All right. See you on Thursday.